Welcome. This is a recorded session of the Post-Quantum Cryptography Conference of the PKI Consortium, which took place in Kuala Lumpur, Malaysia. This conference is made possible through the support of the PKI Consortium Post-Quantum Cryptography Working Group and our sponsors SSL.com, Entrust, Keyfactor, HID, and Crypto4A. And with exceptional organizational support from SSL.com, Keyfactor, Logius, POS Digicert, Baker Tilly, MSC Trustgate, and Digitoris. Join the discussion. Join the PKI Consortium. Go to pkic.org/join.
So our last speaker today is Volker Krummel. Volker is a senior technologist with Utimaco, a practice leader in this area. He's had years of experience applying cryptography to government and financial services. His conversation today on a practical application of stateful hash schemes is both a discussion of the subject as well as building on innovation and evolution of this technology since our last conversation here a year ago at PQI. So without further ado, Volker Krummel.
Thank you, John, for the nice introduction. Thank you for having me here. So as already advertised, the topic is here about the stateful hash-based signatures, about the new achievements that we made in the last year. And the personal mission of this tour is to make this stateful hash-based signature as convenient as possible, not more, but as convenient as possible to make them usable, because they have certain very, very interesting properties that we think we will like very much to see in the field. So first we start with a short recap, because I assume not everybody is familiar with the notion of stateful hash-based signatures. We do a brief recap, and then we dig into the new topic and the new achievements. So stateful hash-based signatures, recap here, typically the construction is something like you design first an OTS scheme, a so-called one-time signature scheme that you can use at most once to sign one piece of data. So one public key, one private key, one piece of data, one signature, then it's done. If you use it twice, the security of the signature is typically broken. So it's very limited in the usage. To make it more applicable to the real world use cases, of course, you can multiply these approach, having multiple of these OTS schemes in parallel. Still dealing with the challenge of having different public keys for the verification side, which makes them practically unusable. And the main idea that came up already in the 1970s is something like, hey, you can hash together all these public keys to end up in a commonly shared public key. So then you end up in a signature scheme that is able to sign a limited number of signatures, but the verification is done with the commonly shared public key here at that side. So seems a bit complicated, but it's a very basic, a very mature design. The security of this design just relies on the security of the underlying hash function, which is the best we can get at the moment from a security perspective. The only little drawback is, as I said before, we are building that stuff upon OTS schemes, so one-time signature schemes, and I need to keep track of the usage of that key, as I indicated in the slide here. Pointer doesn't work, but doesn't matter. So we have to cross out all the OTS schemes, the OTS keys that we used during the lifetime of the key, and be aware of what would be the next potential OTS key to be used. So this is the basic, let's say, challenge, or the basic topic behind what we call state handling. So you need to be aware of that. This is one part. And of course, the other limitation of these part or point of algorithms is the limited number of signatures. The tree can be quite large, so height of 20 or 25 are commonly used in practice here. So you get 2 to the 20 or 2 to the 25 different keys, make it applicable in use cases like firmware signing and all these, let's say, more or less static scenarios, for example, root CAs and the like. The challenges that are with this state handling, which doesn't look too complicated in the first side, so it's just keeping track of what you did in the past. Let me show you two, let's say, examples where this provides a challenge. First, it's a backup and restore scenario. So it's a good practice if you run an HSM, if you run a cryptographic instance, to make a backup before starting your use case, your services. And exactly here comes the state property into play. If you just use it as you want to use with a stateless key and the stateless algorithm, you run into trouble if you restore that backup in a later point in time, because you regenerate a state that you already passed by, and this would make it possible to reuse one of these OTS keys and break the security of the overall scheme. So backup restore is a problem here. And the second is, of course, the use case that we see in reality typically are not static ones and centralized. They are decentralized in the sense that you have to split your key to different instances, and you have to do it in a secure way to prevent the reusage of one of these OTS keys. So this is the basic, let's say, setting of what we have to deal with. From a problem side, from a benefit side, we will get the most major algorithms that we have so far in the PQC field, or in the whole crypto field for signatures. So we proposed already last year, so this is still the recap, properties that an OTS preserving scheme should fulfill. And we propose here to not only focus on the security, which is definitely the paramount. So you should not run these major signature algorithms and just do a shortcut on the state handling, because this will render your security completely or put it on high risk. So the security view on that side is quite clear. So we need some kind of comprehensive design, which we always need, especially in the context of HSMs. We suggest that you separate the state information from the key information to make your solution or the potential solution more flexible and maintain the security properties for these different types of information. Yeah? So the confidentiality for the key and also the integrity and the OTS preserving for the state information and things like that. So we don't have to go through all of these properties. What I highlight or want to highlight here is that we also have to take into consideration the operator's view, because handling the state, even if done securely, puts some burden on the operator's side and on the design of use cases. So, for example, we also don't have to go through this list as it is a recap, but it's something like we don't have to rely on synchronous communication between these instances, between HSMs. We don't want to have master-slave architecture here, because this will generate a single proof of failure and things like that. So just taking this into consideration helps us to put this into action, and this is already in the field and in action for very conservative use cases. Just to finalize the recap, this slide is maybe also already known by some of you. Just an example how this stuff works. So assume we have a use case with three manufacturing sites, headquarter and manufacturing site A and B, and we want to distribute such a stateful hash-based signature key among these sites. So what we can do with the OTS preserving framework, firstly, is to set up a trust relationship between these HSMs that are installed on each of these sites. So this is the basic stuff. This trust relationship is based on symmetric cryptography to meet the maturity of these approaches. And then you're ready to go to enter the operating phase with an OTS preserving communication that allows us to shift, to transfer information from one side to the other, back and forth, as we like during the lifetime, the full lifetime of the use case. and preserves the OTS property. So we guarantee if you use that protocol, that framework, you cannot do anything wrong. So the OTS property of all these keys is preserved. And then on each side, as we saw before, the local state management, you're just following a pointer or a checklist. Hey, this key is already used and this is not used. This is quite straightforward. So you can enter the key generation process, for example, an LMS key or an XMSS key consisting of these 8 OTS keys, the one-time signature keys. And then you can start to distribute these keys, these parts of the key to different sites, just from as you like, as the use case demands. You can transfer them before starting the use case, but also during the lifetime of the use case. You can add and remove HSMs to this trust relationship, so building up new sites, steering down sites, and things like that. Blocking attacks is of course mandatory for this protocol. You can also store, let's say, information outside the reach of an application, so that you can even prevent faulty applications to consume all your keys and things like that. So this is more or less the recap. This is stuff that we implemented in the field. The experience that we got in the last 1.5 years about this state handling in context with the LMS and XMSS algorithms is quite convenient. Makes the effort and the security of using stateful hash-based signatures was a big improvement from our side, because installing a stateful hash-based signature is quite straightforward. Dealing with a state over the lifetime of that key, which is typically long-term security, so we are talking at least about 15 to 20 years, is quite a challenge. And addressing it in that way is really helpful on that one. So what we do in the last let's say half year to improve this approach is to get really a security proof. So the design of the system is quite mature and quite conservative. But of course, what we also want to have is a security proof that our state handling mechanism that I presented so far is really secure. And we did this proof in the context of the universal composability model. This is a, let's say, a well-known system and mechanism in the crypto world to analyze security of complex systems where you put together different cryptographic primitives, and you want to prove the security so that the security guarantees of each of these blocks is preserved in the overall setting. So just using AES is not enough. You have to use it in a right way and to combine it with other cryptographic mechanisms in a correct way. So we get very strong security properties, and the OTS preserving security notion that we introduced in that model can be proven now. So the proof is ready. The publication is not yet online. Will be online in the next few weeks. So happy to share that as soon as it's out, or just drop me a message if you are interested in the details here. Again, the same as for the white paper for the OTS scheme description, so that you get more information about the familiarity and stuff like that. So saying that, you have a very mature signature algorithm, you have a very mature, let's say, state handling companion here in that setting. So this is all about security, but what about automation and convenience? So giving the security on the level inside of secure hardware allows you to automate things that are outside of the security boundary. For example, automation of key distribution here. So here we see a setting that is more or less standard setting. We have an application on the left side. We have some kind of HSM racks on the right side for redundancy, on different sides maybe. And of course, the application want to use the HSMs for signing and for achieving the security goals on that side. We also see, well, this is typically overlooked, the operator on the right side, on the side that they are responsible for running the HSMs and the crypto infrastructure. And of course, as I said before, shifting keys, shifting state information from one HSM to another is at least an additional burden that you get with these stateful hash-based signatures. So here, as we introduce the security completely and manage the security completely in hardware security modules, so the operator cannot do anything wrong on the outside, we can simply elaborate that system a bit more to introduce so-called state management policies that are policies like, distribute evenly the remaining keys of the scheme over the existing HSMs, for example. So assume that HSM1 in this scenario is consumed, let's say, a larger number of signature schemes or signature keys here. The SM policy in general can automate the transfer process from other HSMs so that at the end of the process, each of these HSMs has again the same number of keys remaining here. So what we achieve and what we can see on a high level from a view is, from an application side, the application does not have to take care about state handling and about shifting keys and things like that, even though security should also not be, let's say, part of the application. So from the application view, it looks more like stateless, as it could be here. And even from the operator side, you get the full support for automation. So you can introduce your policies, the SM policies, and then you see everything goes like it should be in an automated way. So we as I said, we introduced this stuff into the field, into real world, and we have some lessons learned how to improve the key generation and the signing process of stateful hash-based signatures. Let me just share two of these ideas here. For the key generation, typically you need, as we saw before, you need to generate the OTS keys sequentially, one by one, and then you're able to build up this tree to compute the corresponding public key for that. Yeah. So starting the OTS key generation, and then you have this tree in the back, and then you can see how you combine all these information, compute the nodes of these trees, and then you end up with a public key, the commonly shared public key as a root of that tree. So that's clear. As I said before, this tree can have heights of 20 or 25, so it's quite a large number of OTS keys, and it can take a long time to generate these keys in sequence. So of course the straightforward approaches that we implemented is to distribute this key generation onto several HSMs, onto several instances. Of course, obviously giving you a speed up factor of the number of HSMs that you can use in the key generation process. So you can select your parameters, you can generate these seeds, and then you can do this exactly the same process. Again, if you dig a bit deeper into that, of course, the generation of the tree based on partial knowledge of OTS schemes has to be addressed, and these information that are used in the tree to generate the public key has to be shared between these HSMs. Yeah? Since all the nodes represent public key information only, this is not a, let's say, confidentiality concern here. So you can speed up the key generation process by the factor of 10 using the system that we saw before. You can exploit, for example, 10 of these HSMs for the key generation process, and you could transfer that key to different HSMs, or even reduce the number of HSMs that can use these keys in a later point in time. So you are quite flexible in scaling up the key generation process and reducing the HSMs or the instances that do this for the generation and for the use case. The second part that we learned about improvements here, typically speed improvements, of course, is the signature generation. Even if you distribute the key to different HSMs, for example, HSM1 and HSM2 here, the signature can be computed completely in parallel. So HSM1 now signs the light blue document, computing the light blue. I'm not sure if you can see this quite well, but computing the light blue nodes in that tree as an add-on information to this OTS signature, which allows the verifier to verify the signature giving the shared public key. And of course, you can do it on the other side. So just using different OTS instances, different OTS keys on the LMS key, and that's it. So this is straightforward if you can distribute that key. What we improved also here is that we want to improve the data management of the quite large key or tree information on that one. So we thought about doing the outsourcing of the tree handling completely. So the tree only stores public information, and in principle, this doesn't have to be stored inside of an HSM. So you can think about having an HSM infrastructure, having HSM1, HSM2, but the tree is stored outside on a server. The HSM is doing only this, let's say, security-related signing operation involving the private key, and all the public key enhancements that we need, especially the nodes from the tree, can be added on the outside. So as we saw before in this example, we can sign these documents exactly in the same way, but the nodes that are used for the authentication path that is added to the OTS signature is enhanced on the outside. This reduces the payload to the HSM, so a lot of data and pre-computation that is needed can be outsourced. And it's a classical trade-off between, let's say, data storage and computation time. Yeah? So we improve speed of the computation of the private key because of this, and we also improve the speed of the signature process. For example, if you think about use cases where you have a very, very tight, let's say, time constraint of computing signatures in a row. And as I said, it's an external storage versus computing time thing. Okay, so just as a summary, what we achieved since the last year's presentation here is we have this OTS preserving framework. We put it into action, into the field. We can now prove, or the design was already, let's say, security oriented. We can prove the security in the UC model. So security is not an issue. Here we have this state management process overhead addressed, so you can automate as much as possible. We address the performance, let's say, challenges of these schemes, especially for the keygen, which can really take a long time. And we also address this data management. So either you have to store the tree with could be some gigabytes, or you have to pre-compute the next known nodes here. What is still open, of course, and what is an inherent feature of these algorithms is the limited number of signatures. Either your use case, you can have a proper estimation, so that it's not an issue for your use case, or as an alternative, we recommend to go for the SLH DSA, which is a stateless hash-based signature. Which has certain different other properties, but also security is based on the security of the underlying hash function. And the point that is still a bit vague and a bit open, but is also addressed from a current standpoint, is the regulation. So the NIST 800-208 paper typically addresses the state handling in a very restrictive way. It's currently under revision. So the current version does not allow you to export any key and state information, which could be addressed here in this scenario with distributedly generating these keys directly from the beginning. But we expect a revision here of this paper that also allows and empowers our solution for the state management here. And with that, I'm quite hopefully on time and not too far away from the lunch break. Thank you very much.
Hello. So with respect to the hardware that you are using, what is the entropy source or is used for the key generation and all?
So, of course, as always, the entropy for key generation is the crucial part. This is exactly one of the reasons why you should use hardware security modules that provide a true random number generator or a certified cryptographic random number generator to be able to create high quality keys. Yeah. So these schemes, especially for key generation and especially for the state handling, they should require and should be run into secure hardware and not in software.
Hey, Volker, great presentation.
Hi.
Sorry for the question, but in the distributed setup you showed throughout manufacturer 1, 2, and the headquarters, what happens if one of the sites is losing connectivity?
So connectivity is not an issue here. It's maybe I go back to that slide. So what we need is, of course, some kind of connectivity between these sites, but this connectivity is, let's say, a logical connection. Yeah, so you have to be able to, in principle, transfer data. It could be a network connection, could be file transfer, whatever. Depending on your constraints, on your use case, of course, you should be aware that this connection is established whenever you need to transfer something. But there's no need for a real-time, let's say, online connection. So there's no handshake, there's no sync or online sync between these sites. They are completely autonomously working, and only the, let's say, interaction is when I want to transfer some information, I will send it from site A to site B. At a certain point in time, site B receives the message and then can use it. And as long as it doesn't receive that message, of course, obviously, it cannot use that part of the key. Yeah? But it's very, let's say, conservative and very flexible. Great.
Just 1 second. I need to look it up first. Just came in, literally. Question is from Scott. How to take a trade-off? You can store only part of the Merkle tree on, say, level 15.
Yes. So what I presented here is the extreme that we completely or store the complete tree outside. And of course, as Scott mentioned, we could have a trade-off here. This is currently so the outsourced tree could be stored partially still inside of the HSM. So the lower levels, for example, that are directly tied to ODS schemes could be still stored inside of an HSM. So you are completely flexible in putting everything outside, putting everything inside and everything in between, layer by layer, or following, let's say, a smarter policy could be possible. Yeah, definitely.
Any more questions from the audience? Good. Thank you, Volker.
You're welcome. Thank you very much.
Tremendous presentation. Very rich. It's really reassuring to see the level of invention and innovation that you're bringing forward. I'll say in advance, I look forward to your update next year to see how you're advancing this technology even further.